Okay, so we're back and still looking at probability. More specifically, in this video, we're going to focus on mutually exclusive and independent events. Now, these are two specific relationships that events might have, and we're just going to look at what they mean in context, and we're going to look at how that might affect our options when it comes to calculations and problem solving if we know these two relationships exist. Let's start with mutually exclusive. If two events are mutually exclusive, they cannot happen at the same time. These events will be conflicting events. These events will clash with each other. These events will be in disagreement. So some examples, just some popular ones. If you flip a coin, so that's your experiment, the outcomes of achieving a heads and achieving a tail, or the event achieving a head and the event achieving a tail, are going to be mutually exclusive from each other. They cannot both happen at the same time. There is no outcome that fits both of those two events. If you roll a dice, the rolling of the dice being your experiment, two events would be to get an even number, to get an odd number. Each of those have three outcomes within the event, but there is no overlap between any of those outcomes. The events rolling an even number and rolling an odd number are mutually exclusive. They are in disagreement. There is no overlap. There is no agreement between them. These are clashing events. If an experiment was to see whether or not a student arrived to school on time, two events are student arrives to school on time and student arrives to school late. These are mutually exclusive events. They cannot happen at the same time. So let's get a little bit more mathematical. If we have two mutually exclusive events, then the probability of A and B happening is going to be 0. We've already said it's impossible. We represent impossible numerically with the number 0. Additionally, we can say the probability of A or B is simply the probability of A plus the probability of B. If we add them together, that would be the probability of A or B. On a Venn diagram, this is what it would look like. The two events are just separated. There's no overlap. There's no intersection. We make sure we draw these circles to not be touching. Technically, you could draw them overlapping, but you would put a 0 in the intersection. You would put a 0 to show there is nothing that is both in A and in B. But it just makes sense to draw them separately, so there's no ambiguity, so there's no misunderstanding. Okay, let's go through a situation here. If I'm told that event A and B are mutually exclusive, I'll start with a Venn diagram as shown. Probability of A is 0.2. I can put that into the circle for the set 0.2. Probability of B, 0.4. I can put that into the circle for the set B. And there are no other regions to consider except for outside of the circle. So quite simply, in my head, I know all of these probabilities should add up to 1 since probabilities are exhaustive. And I'm just going to put in a 0.4. All right, perfect. Question. If I'm asked to find the probability of A or B, just like we saw above, it's the probability of A plus the probability of B. That's going to give us 0.6. Okay, so this is only true if we know that they're mutually exclusive. It's really important that you track the identifying relationship and then you can use your calculations appropriately. A much easier calculation than you would have if the events were not mutually exclusive. Next, we're asked to find the probability that an outcome is event A but not event B. So usually we would look at circle A and just try to consider everything that was outside of circle B. Well, since there's no overlap, we're just looking at the entirety of circle A. So the probability of A but not B is the probability of A, which is 0.2. And in the last part here, we've been asked to find the probability that it's neither A nor B. So luckily we did this just instinctively right at the beginning in completing the Venn diagram. But this is the probability is not within set A and it's not within set B. So we do 1 minus the two known probabilities, the two regions we're not interested in, and that gives us 0.4 once again. So here's a bit more of a formal way to show what the probability would be. So that's mutually exclusive, and we'll come back and look at some more worked examples, some different situations that we might come across with mutually exclusive events. That's one type of relationship. Another type of relationship we need to be aware of and being able to identify is when we have independent events. Two events are independent from each other if one event does not affect the probability of the other event happening. For example, if I was to flip a coin and I got tails on the first flip, and then I flip the coin again, the outcome of tails the first time round has absolutely no impact on what's going to happen the second time I flip the coin. Each flip of the coin is independent. What happened the first time does not affect what happens the next time. If I was to roll a dice and flip a coin, the outcome on the dice has no impact on the outcome on the coin. These two events would be independent. If I had a selection of chocolates in a box and my favorite chocolate was a Mars bar, and I asked somebody to pick a chocolate at random and they were allowed to eat it, if I did that 5 times before I made my selection, everybody's selection before mine does actually have an effect on my selection. They've changed the probability that I get my favorite chocolate when I dip my hand into the box. Because they've taken the chocolate and they have not replaced it, the box of chocolates is no longer in its original state. So that's a non-example of independent events. That is an example of where previous outcomes will affect subsequent outcomes. So just be on the look. Within the scenario, are we looking at independent events or are we looking at dependent events? Okay, so just once again, formally, there is a way to identify independent events, and this is true if we know something's independent, and it's a way for us to test whether things are independent. If two events are independent, the probability of A and B will equal the probability of A multiplied by the probability of B. The intersection, the probability of them both happening at the same time, is going to be the product of each of them happening individually. Okay, let's just go through an example. I roll a fair dice once and record the number showing what is the probability. And before I even get to the probabilities, let's look at the sample space for a dice. We know that there's 6 outcomes and they're equally likely. What is the probability that I get a multiple of 2? Well, here are the multiples of 2, 2, 4, and 6. So the probability of a multiple of 2, that's 3 out of the 6 options. So that's 1/2. What is the probability I get a multiple of 4? Well, only one of the outcomes is a multiple of 4. That is the number 4 itself. And that has a probability of 1/6. Now, my conceptual explanation of why I know these two things are not independent is that if I was to achieve a multiple of 4, then it's already a multiple of 2. So there is some link between the two outcomes. And whether one happens influences whether or not the other happens. If I rolled a multiple of 4, I definitely have a multiple of 2. And if I roll a multiple of 2, I've got some chance of having a multiple of 4. If I didn't roll a multiple of 2, then it would be impossible to have a multiple of 4. So these things are linked and there is quite a connection between them. Now in part D, we're asked to show that these two events are independent. Now this is a spectacularly popular exam question and you just have to follow this format every single time. Start with a statement that says these events are independent if the probability of A multiplied by the probability of B equals the probability of A and B. You have to have that statement. We're going to follow this up with numerical evidence, numerical calculations. I'm going to start by identifying the intersection and checking to see whether my calculation matches. So the intersection of A and B, is going to be 1/6. I can see that from my sample space diagram. And now my calculation, a half times a sixth equals 1/18, 1/18, which is not equal to the intersection I'd already identified. From there, I can conclude these events are not independent. They needed to match for it to be independent. They needed to match for me to have proved we had independent events. Just be mindful about how independent events are drawn. We do draw them with an overlapping circles, but this does not mean that every time a Venn diagram has overlapping circles that the events are going to be independent. We have to use the test of independence. Only if the probability of A multiplied by the probability of B equals the intersection do we have independent events. You cannot tell just by looking at the way the Venn diagram is drawn. You can for mutually exclusive because there's a big gap between the two events, but there's no visual indicator as to whether or not two events are independent. You have to do the test. So in this question, we're told that the Venn diagram shows the number of people who like each of two different colors, color A and color B, and we're asked to determine whether or not these are independent. So as I've said, we start with the statement independent if the product equals the intersection. I'm going to start by stating the intersection. I can see here for myself the overlap. There are 4 people here, so a frequency of 4. I need to quickly just calculate what the total frequency is. So that's 15. 4/15 is the intersection. I'm going to calculate my product. So that's the probability that somebody chose color A multiplied by the probability someone chose color B. So that's 10/15 multiplied by 9/15. I can simplify this in my head quite quickly. That becomes 2/3 times 3/5. I can do the whole calculation in my head. 6/15. 6/15 does not equal the 4/15 that we know the intersection is. The product does not equal the intersection. So we can conclude that therefore these two events are not independent. Okay, so in this question, we're now told that there are 3 events, A, B, and C. And this is going to happen quite regularly. It's rare that we'll get a 4th, but 2 and 3 are the common number of events, number of sets we'll be working with when it comes to probability and Venn diagrams within the course. The events A and B are mutually exclusive, and we've been asked to draw a Venn diagram to represent that. I'm going to start with the mutually exclusive events. I'm going to start with the A and the B, and I'm just going to draw them unconnected. There needs to be space in between them. Next, I'm going to draw a circle for set C, for event C, and this will overlap with both A and B. Now, I've not been told whether A and C are mutually exclusive. Neither have I been told whether C and B are mutually exclusive. So for now, I'll assume that there is some sort of overlap between them. We might find out different later on. So that's my Venn diagram. Happy with that. We're told if the probability of A equals 0.1 and the probability of B equals 0.6, can we determine the probability that it's neither A nor B? Well, neither A nor B is going to be any of the space outside of circle A or outside of circle B. So I can just shade that in quickly so I get an idea of what I'm looking for. Okay, so the only thing unshaded is A and B. So if I subtract the probability of A and B away from 1, I should find the probability of the shaded area. So even with minimal information, we can go ahead and get a numerical answer. 1 minus 0.7 equals 0.3. Okay, so here once again we're working with 3 sets in our Venn diagram. This Venn diagram shows the number of students in a particular class who watch any of 3 popular TV programs. In part A, we've been asked to find the probability that a student chosen at random watches B or C or both. Okay, so just looking at the frequency values within B or C, I'm interested in the 4, the 5, the 10, and the 7. So let's add those together, and that's going to be out of the total number of students represented in this Venn diagram. So it's going to be that sum over 30. 26 over 30 cancels down to 13 over 15. So the probability of B or C, 13 over 15. Second part of the question. Determine whether watching A and watching B are statistically independent. Okay, we should be getting used to the structure here. We know they're independent if the probability of A times the probability of B equals the probability of A and B. I'm going to start by stating the probability of the intersection. Probability of A and B is 4 out of 30. Let's see if our calculation matches up. Probability of A, well, that's going to be 3 plus 4 over 30. Probability of B, 4 plus 5 plus 10 over 30. That gives us 7 over 30 multiplied by 19 over 30. 133 over 900. And that is not equal to 4 over 30. We can conclude, once again, that these are not independent events. You need to have the structure every time. You need to state the relationship you're using, you need numerical evidence, and then you need the comparison between the answer you got and what the intersection should actually be. And we'll finish up with a slight twist on that. Rather than being asked to prove or to show events are independent, we have been told they're independent. So we're still going to use the same relationship, and since we know they're independent, we know that the product of the probability of A and the probability of B should equal the intersection. Okay, looking at the Venn diagram in front of us, the intersection is X. Let's see what we get when we multiply out the product. So the probability of A is X plus 0.3, probability of B X plus 0.2, and they should equal the intersection, which was X. I think and hope you can see where we're going. We have a quadratic expression here. Let's expand those brackets. We're going to rearrange to get it into the general form. And from here we should be able to solve by any method you're happy to solve by. X either equals 0.2 or it equals 0.3. And you could go ahead and substitute X into set A and set B, and you could do the multiplication and we would get your specific answer for X. Okay, so two relationships we've looked at today, mutually exclusive and independent. And just to make sure that you can calculate, you can understand in context what it means to be the both of those.